after defining the notion of surface area, we can also define surface integrals. So we're going to consider the integral of a function of x, y, and z on the surface S. And our motivation is that F can represent the density of a thin metal plate in the shape of the surface. And then we want to find, say, the mass of that plate. Well, to find the mass of the plate, okay, we could break up the surface into, again, smaller regions. And then we can find the mass within one of those regions. So say we were interested in the mass inside that region there. Well, we could say that a little bit of mass is the density times a little bit of area. In other words, it would be my f of x, y, z, my density, times the area of a little bit of the surface. So we can think about this piece as being a little bit of the surface. Well, if I parameterize the surface, okay, so I think about this as being a surface R of UV, then I can evaluate F at R of UV, and I'm thinking about that as being U sub I, V sub J. And then the area of a little bit of the surface, we know, is R sub U cross R sub V. The magnitude of that, delta U delta V. And so total mass is going to be approximately a double sum, over all of the little bits of mass. So a double sum over the density times the area. And if you let delta U and delta V go to 0, then what you have is what we call a surface integral. So the surface integral of f ds is defined as a double integral over the region R of f of R of UV. So the density evaluated on the parameterization of the surface times, and then that little bit of surface area. So we think of ds as being RU cross RV du dv. So this we think of as being ds. A little bit of area of the surface. So let's do another example. That example is we're going to let f of x, y, z equal y plus z plus 3. So it's going to be that function. And it's part of the plane z equals 2x plus 3y that lies inside a cylinder. And then we want to evaluate this surface integral. So here, the first thing we want to do is we want to rewrite f of x, y, z as just a function of x and y. So this will be y plus, and then z is 2x plus 3y. So if we're going to be on the surface of that plane, then it's going to be 2x plus 3y. And then we're going to add 3. And so this becomes 2x plus 4y plus 3. So my function on that surface, z equals 2x plus 3y, is just 2x plus 4y plus 3. But then we need to figure out what that ds is. So we need to figure out, again, the magnitude of the normal vector. So another way that we can write this, right, is the magnitude of the normal vector. Okay, so the magnitude of the normal vector, okay, is minus z sub x, so minus 2, minus z sub y, so that's minus 3, and then 1. This makes sense because z is a plane, and we can think about that function as being negative 2x minus 3y plus z equals 1. And of course, the normal vector is negative 2, negative 3, 1. Okay, so that's actually the normal vector. And then I want to find the magnitude of the normal vector. And that magnitude is going to be the square root of 4 plus 9 plus 1, which is the square root of 14. Okay, so now I'm finally ready to kind of set up my surface integral of f ds. So that's going to be a double integral over the region that lies inside the cylinder, x squared plus y squared equals 9. So I'm going to write this as x squared plus y squared less than or equal to 9. I'm going to integrate the function f, which is 2x plus 4y plus 3. And then that's times the square root of 14, the magnitude of n, dx dy. Well, this is an integral over a circular region, so that means I really should do this in polar coordinates. So I'm going to rewrite this integral as the integral from 0 to 3, the integral from 0 to 2 pi. Okay, x is going to be 2r cosine theta. And then with the y, I'm going to get plus a 4r sine theta plus 3. And then this will be r. And then I'm going to do the integral d theta and then dr. So this is the square root of 14 times the integral from 0 to 3. And then I'm going to integrate with respect to theta. So I'm going to get 2r sine theta and then minus 4r cosine theta and then plus 3 theta. Okay, all of that times r, or all of that evaluated between 0 and 2 pi, and then that's times r dr, since the r had nothing to do with the theta integral. Okay, so that's going to be the square root of 14. And then here, if you evaluate sine theta at 0 and 2 pi, you're going to get 0. So this, when you evaluate, just becomes 0. And if you evaluate cosine theta at 2 pi and then subtract evaluating cosine theta at 0, okay, cosine of 2 pi and cosine of 0 are both 1. So when you do this evaluation, this in fact will also become 0. And so what I'm left with is just evaluating the 3 theta. So I'm going to get, see here, the integral from 0 to 3. And 3 theta times 2 pi is going to give me 6 pi. And then I'm going to have r dr. So that's a nice simple integral to do. So I'm going to get, let's see, the square root of 14 times, it says 6 pi r. I'm going to integrate with respect to r and get 3 pi r squared, evaluated between 0 and 3. And so finally, substituting in r equals 3, I'm going to get a 9 for r squared, so I'll get 27 pi root 14. And when I evaluated 0, I'm going to get 0. Okay, so this integral, which could represent, say, the mass of that part of the surface, if f represents the density, okay, this surface integral turns out to be 27 pi square root of 14.